Okay, last Tuesday we studied ideal reheat cycle. So in this ideal reheat cycle, we have steam generator, and turbine, and this turbine has two stages. The first stage is high pressure turbine, and the other one is low pressure. And we have a condenser and pump. So steam that enters this steam generator from this pump is going to receive heat. So there is heat transfer Q that goes into a system, and this steam enters this high pressure turbine. That is number one. And it's going to expand in the turbine and produces power. So there's a turbine power produced by the high pressure, the first stage turbine. And when pressure and temperature of the steam go down, it returns back to this steam generator to receive additional heat. So that is number two. And receiving heat again, Q in. By the way, at the inlet of the steam generator, that is state number 6. So we can say this Q in is process from 6 to 1, and this heat transfer during the reheat process is between 2 and 3. So I can say Q in 2, 3. And once it receives heat, this one return back to the second stage turbine, which is number 3, and produces power W dot T, but this one at this time low pressure. And then any waste heat is going to be rejected in the condenser.
which is number 4, we are rejecting heat Q out between 4 and 5. I can say Q out between 4 and 5. And this pump, to run this pump, we need to provide pumping power W dot T. So this is a reheat process. Then how can we study their performance? We can determine the thermal efficiency. This thermal efficiency can be determined by desired output over required input. And what is desired output? The net power. And required input is Q that goes into the cycle. So we have W dot net is going to be, we have 3 powers. So W dot net can be W dot T in the high pressure turbine plus W dot T produced by low pressure turbine minus the pumping power that we need to provide to run this cycle, divided by, we have 2 Q-ins, Q-in between 6 and 1 and Q-in between 2 and 3. Q dot in between 2 and 3 plus Q dot in between 6 and 1. So that's how we can determine the thermal efficiency. If we write this in terms of specific enthalpy, W dot T is going to be the difference in the rate of enthalpy between, so this is high pressure turbine, between 1 and 2. So this one can be determined by M dot between 1 and 2, H1 minus H2, plus W dot T, turbine power produced by this low pressure turbine. It is between 3 and 4. So M dot H3 minus H4 minus W dot T, which is the pumping power between 5 and 6. Between 5 and 6. 6 is greater than 5 because it is receiving power. So it's going to be M dot, it's not H5 minus H6. It is H6 minus H5 because it is receiving power. Therefore, H6 should be greater than H5. Divided by Q in between 2 and 3. So between 2 and 3, this 2 is receiving heat. Therefore, H3 should be greater than H2. So Q dot in between 2 and 3 is going to be M dot H3 minus H2 plus between 6 and 1. 6 is receiving heat. Therefore, H1 is greater than H6. So this one is going to be M dot H1 minus H6. You can cancel M dot. Then that's how we can determine its thermal efficiency. Okay. if we study this reheat cycle on a TS diagram, and temperature, specific entropy, we have how many pressure values do we have? 1, the highest pressure, HP. So it's going to be between 1 and 6 because steam generator is constant pressure process. So 6 and 1 is going to be at highest pressure, at the highest pressure. And 2 and 3 is going to be the low pressure of the turbine, and the lowest pressure is going to be between 4 and 5. That's the condenser pressure. So there are 3 pressure values available. The first one is the pressure by the pressure of this steam generator. It's going to be between 6 and 1, and the condenser pressure between 4 and 5, and the pressure during the reheat process between 2 and 3. So there are 3 pressure values. We have the highest pressure, intermediate pressure, that is the pressure of reheat process, and the lowest pressure, this is the condenser pressure. So this is pressure by condenser, pressure condenser. And this is the pressure during the reheat process. And this is the highest pressure, steam generator. And we assume that, you know, this at the end, at the exit of this steam generator, we have superheat vapor. So let's start somewhere here. So on this TS diagram, superheat vapor is here. So I'm going to select somewhere, maybe this one. That is the starting point. That is the turbine inlet pressure. Say number 1 right here. And we have high pressure turbine first, and we expect that there should be isentropic expansion. Isentropic means entropy S remains constant. So it should be on this vertical line. So there's an isentropic expansion down to the reheat pressure. So this is number 2. And this number 2 goes back to the steam generator and receiving heat at constant pressure. Receiving heat at constant pressure. Since it is constant pressure, should be on this line and receiving heat. So its temperature goes up this way. Then there is a number 3. So we just receive the heat, and this number 3 return back to this turbine, but this time low pressure region. And there is an isentropic expansion in the second stage turbine. So entropy S remains constant. So it's going to be a vertical line down to the condenser pressure. So there is number 4. So number 4 enters condenser, this condenser, to reject any waste heat. So because of that, and by the way, this condenser works at constant pressure. So this number 4 becomes saturated liquid after losing heat to the surroundings. So there's number 5. And this number 5 enters this pump so that its pressure goes up to how high? To the pressure of the steam generator at isentropic process. So isentropically, pressure goes up to the pressure of the steam generator. So straight line up to here. That's number 6. And in the steam generator, this number 6 receives heat. Therefore, its temperature goes up at constant pressure. At constant pressure on this line goes to number 1. So this is how much net power this Rankine cycle, ideal Rankine cycle, can produce. And the work, the additional power produced by this reheat cycle because of this reheat process is going to be this much. So this is the additional power we can produce during this reheat process. Okay. So this one slide shows everything about the ideal reheat process. We have a couple of problems at the end. So we will study 2 ideal Rankine cycles. One is a standard ideal Rankine cycle. The other one is a reheat cycle. So we are going to practice this cycle together today. Okay. So I think that's about it. We have one more, which is called supercritical ideal reheat cycle. Supercritical means there's nothing different from this one, except the pressure of the steam generator goes beyond this saturation curve. So this is the saturation curve. And if the pressure of the steam generator goes beyond this saturation curve, like this, that is supercritical reheat process. So supercritical reheat cycle can add this much net power to the standard reheat cycle. So the idea is that we are modifying the ideal Rankine cycle to maximize the enclosed area, because this is how much we can produce. So if we have everything like the reheat process, supercritical process, and everything, then the maximum practical thermal efficiency is up to 47%, which is extremely high, considering the energy conversion efficiency of the solar panel in a commercial scale is only 10 to 15%. So that number is very high. Okay. So I think that's everything about the ideal reheat cycle. A few things that that we can discuss. Then, what is the difference between the ideal reheat cycle and actual Rankine cycle? So actual Rankine cycle has much less thermal efficiency, and we just want to discuss what is the reason behind the low efficiency. The low efficiency is due to several irreversibilities where we lose energy due to friction or due to heat loss, and there are many different reasons for this reheat irreversibilities. But the most major, the biggest irreversibilities comes from here, the way we produce high temperature heat to produce steam. So that is the main irreversibilities. So if you want to improve the thermal efficiency of a power plant, this one has the most potential because it has the largest irreversibilities. But what about if we, the limit into this Rankine cycle, the one that we studied in this chapter? If we only, look at this Rankine cycle, the main irreversibility comes from the turbine. The turbine. So in reality, the actual, the power a turbine can produce can be determined by this one. What is this one? Isentropic turbine efficiency that you studied in chapter 6. So in reality, the actual turbine may not be an isentropic turbine. So, we are going to use this isentropic turbine efficiency to show the difference between ideal Rankine cycle and the actual Rankine cycle. So what happened is that, the standard TS diagram, the TS diagram for standard Rankine cycle, ideal Rankine cycle, without this, the steam generator or reheat process or, the supercritical, the fluid, the simplest one is going to be look like this. We have boiler pressure and condenser pressure, and this is what happens. This is the simplest Rankine cycle. So this is the ideal Rankine cycle. In reality, the turbine is not isentropic turbine. So there is increase of entropy. By this much. And this boiler is not constant pressure process. In reality, pressure goes down. And same goes to the condenser, pressure changes. And pump is also not an isentropic pump, so there's an increase of entropy. So in reality, this is what happens. And this green is the ideal Rankine cycle. This red is what happens in reality. Okay? That's everything. So to show the difference between isentropic turbine and actual turbine, we use isentropic turbine efficiency that we studied in chapter 6 to show the difference between isentropic pump and actual pump. We use isentropic pump efficiency that is also from chapter 6. Remember that I told you that in the final exam there will be, the isentropic efficiency. So it can be either isentropic turbine efficiency or isentropic pump efficiency. Okay. So that's everything about the theory part of this vapor power plants, and we are going to solve a few problems together. Actually, two problems. The first one, the simplest one, just the basic ideal Rankine cycle. So at the exit of the boiler, we have saturated vapor rather than superheat vapor. Okay. So we have a saturated vapor enters the turbine at 16 megapascal, and the condenser pressure is 8 kilopascal, and the mass flow rate of the steam entering the turbine is 120 kilogram per second. So we are going to study this ideal Rankine cycle to answer, to determine the net power, the rate of heat transfer, and the thermal efficiency, and etc., etc. Okay, so let's do that together. So whenever you see a Rankine cycle, ideal Rankine cycle, it is convenient to draw the schematic of standard Rankine cycle. So we have a boiler, turbine, and condenser, and pump. And there are four states. Turbine inlet is number 1, condenser inlet is number 2, pump inlet is number 3, boiler inlet is number 4. Okay? And we have how many energy transfers? First, we have a heat transfer to the boiler, Q dot in, and we produces power, turbine power, W dot T. And this condenser rejects any waste heat for the amount of Q dot out. And this pump consumes pumping power, W dot T. So that's what happens. That is the standard Rankine cycle, ideal Rankine cycle. And there are two pressure values. So this boiler is constant pressure process. That means number 4 and number 1, they have the one pressure. P1 is the same as P4 because our assumption for the ideal Rankine cycle, the boiler pressure should be constant. That means the inlet pressure, number 4, and the exit pressure, number 1, should be the same. So P1 is the same as P4, and that is 16 megapascal. And we have condenser pressure. Condenser also runs at constant pressure. That is the assumption for the ideal Rankine cycle. That means P2, the inlet pressure of the condenser, should be the same as P3, the exit pressure of the condenser. So we can say P2 is the same as P3, and that is 8 kilopascal. Then what we need to do? We need to determine the specific enthalpy at each state, H1, H2, H3, and H4. So finding these 4 property values are the first thing that we need to do. So to do that, we need to understand TS diagram. T S diagram. How many pressure values do we have? 2 pressure values. One is the boiler pressure, which is high. So up here, high pressure. And the other one is low, only 8 kilopascal down here. So what happens? At the exit of the boiler, which is the inlet of the turbine, we have a saturated vapor. So where is the saturated vapor? So the exit of the boiler is number 1. The inlet of the turbine is number 1. So the number 1 should be saturated vapor at 16 megapascal. So this one is 16 megapascal. This one is 8 kilopascal. on this 16 megapascal, we have compressed liquid, saturated liquid, saturated mixture, and saturated vapor, and superoid vapor. And we know this one should be saturated vapor right here. So this is number one. Then what happens between 1 and 2? We have isentropic turbine. So the steam expands in the turbine isentropically. What is isentropically? Entropy S remains constant. And what happened to the pressure? Pressure decreases from P1 16 megapascal to P2 only 8 kilopascal on this vertical line. So what happens is pressure drops at constant entropy, so entropy does not change, down to 8 kilopascal. So here is number 2. So this is the turbine, the expansion in the turbine, isentropically. Then what happens between 2 and 3? So heat is removed at the constant pressure. So to be constant pressure, it should be on this line. So this line represents 8 kilopascal. It should be on this line, and it is losing energy because it is removed. So it's going to the left-hand side. How far? Until it becomes saturated liquid. Number 3, saturated liquid. So what happens between 3 and 4? This 3 enters this pump, so its pressure goes up. On what condition? Isentropic pump. So entropy S remains constant, should be on this line. S3 should be the same as S4, and pressure goes up due to this pumping from P3 8 kilopascal to P4 16 megapascal. So the only direction is going to be going up to 16 megapascal, which is number 4. And then in the boiler, receiving heat at constant pressure should be on this line because it is receiving heat moving to the right-hand side to number 1. So this is what happens. Then let's determine H1, H2, H3, and H4. H1 first. H1. H1, number 1 is saturated vapor, and we know the pressure value. So H1 should be H of saturated vapor, Hg. At what condition? We only know pressure, so 16 megapascal. So H1 is Hg at 16 megapascal. So let's find them. Hg at 16 megapascal. We can go to table 8.3, the pressure table, and find 16 megapascal. Pressure table 16 megapascal is, where are you? (16 megapascal is the same as 160 bar, because 1 megapascal is 10 bar. So there is 160 here. And what is Hg? Hg is this one. So the specific enthalpy H1 that we are looking for is this number, 2580.6. 2580.6 kilojoule per kilogram. So that's how you can find the specific enthalpy, H1. Then let's go to H2. What do we know? Oh, we know pressure P2 is 8 kilopascal, but that's it. So can you determine H2? No. So we need to find another way to determine H2. Do we know any other property? Yes, it is isentropic turbine, so specific entropy S remains constant. So can we determine S1? Yes. So if we determine S1, we know S2 and we know P2. If you know pressure and specific entropy, you can determine H2. So that's our plan. So let's find S1 first. We can use the same rule. S1 is going to be Sg at 16 megapascal. So what it is? Sg at 16 megapascal. Sg at 16 megapascal, 160 bar. So Sg is going to be 5.2455. 5.2455 kilojoule per kilogram Kelvin. Okay, then this is S2. So now we have S2 and we know P2, which is 8 kilopascal. And P2 is 8 kilopascal. And what is the phase change process? At 8 kilopascal, compressed liquid, number 1, saturated liquid, number 2, saturated mixture, number 3, saturated vapor, number 4, super vapor, number 5. So number 2 should be saturated mixture. So if you have a saturated mixture, how can you evaluate its properties? You need to know one more property. Since you have saturated mixture, you need to know the quality X. So can we determine quality X? Yes, by using linear interpolation. So how can we use linear interpolation? Since we know S2, so let's use this specific entropy. S2 is SF plus quality X2 times Sg minus SF. That is the linear interpolation that we studied for saturated mixture. So let's solve this problem. So S2 is what? 5.2455. What about SF? Can we determine SF at 16 megapascal? Yes. At 16 megapascal. I'm sorry, it's 2 is 8 kilopascal. My bad. So let's go to 8 kilopascal. I need much bigger screen than this one. 8 kilopascal, where is it? 8.08 is 8 kilopascal because 1 bar is 100 kilopascal. So this is 8 kilopascal. Where is SF? This number. Where is Sg? This number. So let me use these two. SF is 0.5926. Sg is 8.2287. SF is 0.5926. So can you determine X2? Yes. X2 is X2 0.6091. 0.6091. So once you determine X2, now we can determine H by using the same linear interpolation equation. H2 is HF plus quality X2 times HG minus HF, and there is X2. So we just need to find HF and HG at what condition? 8 kilopascal. So let's go to 8 kilopascal. So there's 8 kilopascal. HF is this number. HG is this number. So let me write these two values. Here, this one is 173.88. This one is 2577. This one is 178.88. I'm sorry, 3. Then you can determine H2. So if you calculate H2, you get what? H2 1637.6. 1637.6 kilojoule per kilogram. Oops. So this one is 1637.6 kilojoule per kilogram. So H2 is done. Now what's the next? H3. So what do we have? H3. Its pressure is 8 kilopascal, and it is number 2 saturated liquid. That's good. If you know it is saturated liquid, H3 is going to be HF. At what condition? 8 kilopascal. HF at 8 kilopascal. Can we find it? Yeah, we already did. HF at 8 kilopascal, 173.88. 173.88 kilojoule per kilogram. That was simple. Then the last one, H4. To determine H4, which is the properties of this compressed liquid. The pressure is very high, 16 megapascal. So we cannot assume this H to be close to the specific enthalpy of saturated liquid as we did in chapter 3. And there's one equation that we are going to use that's new in this chapter. That equation is H4, the compressed liquid whose pressure is very high. We can use this equation. H3 plus specific volume V3 times pressure difference B times P4 minus P3. Please make sure that you know you write this one down on your formula sheet and make sure that you use this equation when you determine the specific enthalpy of compressed liquid, which is the exit of the pump. Then we already know H3, this number, 173.88. What about V3? Yeah, we can find V3, no problem. We can use V3 is Vf at 8 kilopascal. So what is it? Specific volume of saturated liquid at 8 kilopascal. At 8 kilopascal, specific volume Vf is going to be 1.0084 times 10 to negative 3. 1.0084 times 10 to negative 3 cubic meters per kilogram. This one goes here. So let me write. V3 is 1.0084 times 10 to minus 3 cubic meters per kilogram. What is P4? P4 is 16 megapascal. I don't like megapascal. 16,000 kilopascal. What about P3? Only 8 kilopascal. 8 kilopascal. So if you do the calculation, you get H4. So H4 is what? 190.01 kilojoule per kilogram. So this is how you determine H1, H2, H3, and H4. So whenever you have a problem in the final exam regarding an ideal Rankine cycle, the first thing that you need to do is you need to show how you calculated H1, H2, H3, and H4. So once you have all these specific enthalpy values, then it's time to solve the problem. What is the first one? The net power developed. So what is the net power? Net power W dot net. So we have, how many powers do we have? The pumping power and the turbine power. The turbine power is the one that we produces, and the pump power is the one that we need to provide. So the net power is going to be WT minus WP. Then how can we determine WT and WP? WT can be determined by M dot times. So WT is the difference between H1 and H2, between H1 and H2. H1 is greater than H2, so it's going to be H1 minus H2. H1 minus H2 minus W dot T. So M dot between 3 and 4. So the pump gives power to H3. So H4 should be greater than H3. So the pumping power, W dot T, is going to be H4 minus H3. So it is M dot H4 minus H3. So that's how we determine the net power. That is part A, the problem A. And do we know M dot? M dot is given 120 kilogram per second. Do we know H1? Yes, this one, 2580.6. Do we know H2? Yes, this one, 1637.6. Do we know H4? Yes. 190.01. Do we know H3? Yes, this one. 173.88. So if you do the calculation, the net power is going to be, where are you? 1.112 times 10 to the fifth kilowatt. So this is the net power developed in this ideal Rankine cycle. Any question? You will see on ideal Rankine cycle in the final exam. Could be just basic ideal Rankine cycle, or the ideal Rankine cycle with steam generator, or the reheat process, or the supercritical process. So basically, you are going to calculate H1, H2, H3, H4, or possibly H5 and H6. So this is exactly what you are going to do in the final exam. Okay? Then what is the second part? The rate of heat transfer to the steam passing through the boiler. So what is that? So the rate of heat transfer to the boiler, this one, Q dot in. So let's determine Q dot in, no problem. B, Q dot in. So how do you determine Q dot in? That is the difference between H4 and H1. Since H4 receives heat to become H1, so H1 should be greater than H4. So Q dot in is H1 minus H4. Okay. M dot H1 minus H4. It's not H4 minus H1 because H1 is greater than H4. Then we know M dot, yes, always 120 kilogram per second. H1 here, 25, 80.6. H4 here, 190.01. So can we determine the rate of heat transfer? Yes, 2.869 times 10 to the fifth kilowatt. Okay, that wasn't difficult. Feel free to, to interrupt if you have any question. The third one, the thermal efficiency. The main question, the thermal efficiency. So how can we determine the thermal efficiency? Desired output over required input. What is the desired output? W dot net. What is the required input? Q dot in. So C, the thermal efficiency can be determined by W dot net over Q dot in. So we already have W dot net and Q dot in. So can you determine that? Yes. 0.388. So 38.8%. The last problem, the mass flow rate of the condenser cooling water. So we want to study the cooling system. So how much, the flow rate do we need to reject heat from the Rankine cycle? So where is the heat rejection? Oh, there it is. Q that out. So we need to determine Q dot out to study the cooling system. So let's determine Q dot out. So part B. So Q dot out first, that is the heat rejection in the condenser. So this Q dot out can be determined by the difference between H2 and H3. Since Q is removed from H2, H3 should be less than H2. So Q dot out can be determined by H2 minus H3. So this is M dot H2 minus H3. So let's calculate this Q dot out. Do I know that? I don't know that. But that's okay. So M dot is 120 kilogram per second. H2 is here 1637.6. H3 is 173.88. So if you do the calculation, calculator 1637.6 minus 173.88 multiplied by 120. So we get 1.756. 1.756 times 10 to the fifth kilowatt. So that much heat should be removed from the Rankine cycle. And according to the problem statement, it says the temperature increase of the water, the cooling water, is 18 degrees Celsius. So this much power should be removed by the cooling system. And how can you determine the change of energy of the cooling water? M dot times specific heat times temperature difference. Temperature at the exit of the cooling system minus the temperature of the inlet of the cooling system. So the temperature rise is going to be 18 degrees Celsius. This whole thing is going to be 18 degrees Celsius. And we can use specific heat value, let's say approximately 4.18 kilojoule per kilogram degrees C, which is kind of common sense. So we have everything but M dot. So can we determine M dot, the mass flow rate of cooling water, 2,335 kilogram per second. So every second you need 2,335 kilograms of water. That is about the same mass of F-150. So that much water you need every second to run a power plant. So that's why, you know, the giant, heavy, these power plants are built near the ocean, so we can use seawater, which is free. So this is a typical analysis for Rankine cycle. This is what you're going to do in the final exam. Any question? Yes. Oh, it depends. So I will, you know, I will check how much time you need per problem. If it is more than, the typical time for the first exam, like the second exam, I may give you 3 problems instead of 4 problems. Yes. We had a discussion about that on day 1, but if you want 2-hour exam, I can do that. So yeah. So if it is 1 hour, 4 problems, 2 hours, 8 problems, and I think that we agreed to have 1 hour exam, right? If you want 2 hours, I can provide my lab space, so you can solve 8 problems instead. But you need to let me know at least a week in advance so I can prepare your own exam with 8 problems. Send me an email about that, okay? Any other question? No? Every remaining homework is due by the day of the final exam. So you have plenty of time. By the time, by the starting time of the exam. So I think the exam starts at 10 p.m. No, 10 a.m., not 10 p.m., 10 a.m., 10 p.m. Sounds crazy, right? My wife is not gonna be happy about that, okay? So 10 a.m., so the final, any homework, any leftover homework, if you haven't submitted them yet, please submit. You can submit late with a small penalty, but the deadline for any remaining homework is going to be 10 a.m. on the day of the exam. I think the 10th of December, right? After that, no more homework, the submission. I don't have time to grade them. I need to plan for my winter break vacation. I won't be here. I will go to the south, maybe Florida or Texas, and until day 1 in spring. No, I will be going sabbatical. I won't come back until summer next year. Oh, that's not it. We have one more problem. I didn't know that. So we have one more problem. So that was ideal Rankine cycle without any modification. Supposed to be pretty simple. I'm pretty sure that you are very disappointed about the difficulty of this problem. So here is a challenging one. So we have a steam generator that produces supercritical, the fluid with reheat cycle. So this, and we have an isentropic efficiency of turbine, isentropic efficiency of pump. So this is like the ultimate boss. So if you can solve this problem without any difficulty, you don't have to worry about any problem in the final exam. So the easiest one and the hardest one. So the exam problem is going to be between these two. Okay. So let's solve this problem. We have a reheat process. So if you have a reheat process, the first thing you can do is draw your reheat cycle. So we have a steam generator, and we have 2-stage turbines, high pressure turbine and low pressure turbine, and the rest of them is the same, condenser and pump. So first, the starting point, state number 1 is going to be the inlet of the high pressure turbine. And this high pressure turbine produces what? Power. Turbine power. W dot T. But that's not the only turbine power. So I'm going to say turbine power from this high pressure stage. And after producing this power, the steam, you cannot rest, go back, work harder. So this is a reheat process. So number 2, goes back to the steam generator and receiving heat. So how much heat? Q in between 2 and 3 and goes back to the low pressure turbine number 3 and produces power W dot T, but this time it's going to be a low pressure region LP. Then your job is over. Go, to have a break. So it goes to the condenser number 4, and we want to reject any waste heat. So there's a Q dot out, removing waste heat, and return back to the pump. Time to work. It's Monday. So number 5, and pump consumes pumping power W dot P and increasing the enthalpy and go back to the steam generator, which is number 6, and receiving heat in the steam generator for the amount of Q dot in 6 to 1. That is what happens. The reheat process. You have 6 states and 1, 2, 3, 4, 5, 6, 6 energy transfer rates. Okay? Then what is the next thing that you want to do? You want to, study TS diagram. So each time when you have a Rankine cycle, always make this one and make this one. TS diagram. How many pressure values do we have? We have a high pressure. Number 1 is high pressure. And this steam generator runs constant pressure. So this one is constant pressure. Constant pressure. Condenser is constant pressure. Turbines are isentropic. Pump is isentropic. That is the assumption for the ideal Rankine cycle. With that assumption, this P1 should be the same as the inlet of the steam generator 6, P6. That is one thing that we know, and we have a reheat process. Number 2, the pressure at number 2 is not the same as P1 because there's a expansion in the turbine, so pressure goes down. And once pressure goes down, it goes back to the steam generator, receiving heat at constant pressure. So P2 should be the same as P3. P2 should be the same as P3. And then go to number 4. Number 4 enters this condenser, and condenser runs constant pressure. So P4 should be the same as P5. So P4 should be the same as P5. So how many pressure values do we need for this TS diagram? 1, 2, 3. So 1, the highest pressure. 2, the pressure during the reheat process. And 3, the lowest pressure, which is the condenser pressure. What is the starting point? Do we have a boiler? No, we have a steam generator. That means that the inlet of the turbine is not saturated vapor. Previously, we had the boiler, so the inlet of the turbine was saturated vapor, but if you have a steam generator, it goes up. So you have a superheat vapor. So on this TS diagram, we have number 1, number 2, 3, 4, and superheat vapor, number 5. So the starting point is somewhere up here. Number 1. And what? Oh, and we have a isentropic turbine. isentropic turbine down to number 2 here, number 2, and constant pressure heat addition 2 to 3 up to this much, number 3, and again isentropic expansion to number 4, and the cooling to saturated liquid number 5, and the increasing pressure to the highest pressure number 6, and it says supercritical system, not following this, going above like that. So that's what happens. Then what do we need to know? What do we need to do? We need to determine the specific enthalpy. How many times? 1, 2, 3, 4, 5, 6. So 6 times. 6 times. So H1, H2, H3, and how many? H4, H5, H6. Sounds fun. So do I have to give you the standard Rankine cycle in the final exam or the reheat cycle in the final exam? No opinion? Okay. Possibly reheat cycle. Then let's determine H1. What do we know? Let's see. Oh, we have information. Steam enters the first stage turbine at 28 megapascal, 520 degrees Celsius. While pressure is much higher than the previous problem because we have a steam generator. So for H1, we know pressure P1 is 28 megapascal and P1 is 520 degrees Celsius. We all know this is set on superheat vapor, so you can go to superheat vapor table and find these two values, 28 megapascal, where are you? 28, 28, 28, oh, right here. 28 megapascal, 28 megapascal. This one is specific volume, specific internal energy U, specific enthalpy H, specific entropy S, and we have a 28 megapascal and 520 degrees Celsius. So this is the H value, 3,192.3. 3,192.3 kilojoule per kilogram. Wow, that wasn't difficult. So H1 is okay. Now H2. Then the steam exits the first stage turbine at 6 megapascal and 500 degrees Celsius. Oh, I'm sorry, 6 megapascal. That's the only thing that we know. So it exits the first stage turbine at 6 megawatt, 6 megapascal. So P2 is 6 megapascal, and we know P2 is the same as P3. So P3 is 6 megapascal, and it reheated at constant pressure to 500 degrees Celsius. So the 500 degrees Celsius is after this reheat process. So number 3. T3 is 500 degrees Celsius. So can we find H3? Yeah. H5 seems to be simple. Directly from the property table. 6 megawatt and 500 degrees Celsius. Okay, here. 6 megawatt, 500 degrees Celsius, 3,422.2. 3,422.2. Oh, it's timed? Oh, I didn't know that. So we found H1 and H3, and we are going to, determine the other 4 specific enthalpies on Tuesday.